Welcome friends. So let us continue our discussion on transient response for series RC circuit. So this is a circuit for series RC circuit that is excited by a voltage source, DC voltage source of magnitude V. Okay. So initially switch S, it is open and it is made close at t is equal to 0. It is closed at t is equal to 0. Now let us try to understand some initial conditions. So since it is open initially, so no current should be flowing through the R and C. I repeat, since the switch is initially open, so voltage source is detached from R and C. So no current should be flowing through the R and C. And due to this reason, since no current is flowing through this R, flowing through this capacitor, so voltage does not appear or voltage does not build up across this capacitor. Voltage does not build up across this capacitor. So before switching, voltage across capacitor is 0. So just after the switching, Vc 0 plus also will be equal to 0. So that is the initial condition. This is because voltage across the capacitor does not change instantaneously. Right? Now, from the another property of a capacitor, that whenever a inductor whenever a switch is closed, then it refers to the transient state or transient condition. Now during transient condition, capacitor behaves like a short circuit. Right? Capacitor behaves like, so it will offer zero reactance path. So due to this fact, since it is offering now zero resistance path during transient state, so that current flowing I0 plus, that will be simply V by R. That means just after the switching, current is flowing V by R. Because capacitor will behave like a short circuit during this phase. Because during a transient state, capacitor behaves like a short circuit. Now we can apply KVL equation. So what is that? V is equal to R into IT plus 1 by C integration 0 to T I dt. Okay. So with that, if you take the derivative, then it will be di dt. This expression becomes 1 by RC IT. That will be equal to 0 because voltage is constant, so it will be 0. Its derivative rather it's 0, so you will get this differential equation. So you will see that this is a very well known form as mentioned in equation 3b previously. This form. Okay, it is stated by Green. So its solution is actually yt is equal to y is equal to a into e to the power minus, sorry, it's not a actually, it is k into e to the power minus at, k into e to the power minus at. That is the solution from the equation 3b, from this expression. What is k? K is the constant of integration. So if you now write down the equation for this. So it will be k into e to the power. Now what is a? A is equal to 1 by RC. So it will be k into e to the power minus t by RC. So in another words, we can say in the same fashion, e to the power minus t by tau. So now in this case, what is tau? Tau is equal to RC. It's again called time constant. So the conception time constant, so conception of the time constant remains same. However, this time for series RC circuit, time constant becomes R into C. Okay. Now you should impose the current or initial condition. So what is that initial condition? At t is equal to 0, at t is equal to 0, what is current? Current is equal to V by R. It is not 0, it is V by R. Okay. So you substitute at t is equal to 0, that means from this equation, that is it is equal to k into e to the power minus t by tau. So with that, when t is equal to 0, then I becomes V by R, k into e to the power minus 0 by tau. So e to the power minus 0 by tau, it becomes 1. So k is equal to V by R. So your equation becomes it is equal to V by R into e to the power t by tau. Similarly, we will get similar equations for VRT. And you will get similar equation for VCT. The expression may be different, but the process are same. Okay. Now, if you recall the previous case, in case of a VLT, VLT expression was like this. VLT, that is the voltage across the inductor. The expression was, it is something V into e to the power minus t by tau. V into e to the power minus t by tau. So that is the expression of VLT in case of previous case. Now you see these two expressions are same. So if you follow that, you see that figure 4c represents this equation. Okay, equation 11. This equation is represented by this figure 4c curve. So the same curve will repeat here for IT. For IT. So similarly, at initially it starts with some current V by R, as it stated here. It starts with some current V by R. At t is equal to infinity, it will be 0. Okay, and some middle portion, let us say this is tau. So it will be 0.368 V. 0.368 V by R. So same response. So this is the case actually, 0.368 V by R. Now if you follow the VRT, it is exactly same nature you will follow. Okay, so it will follow actually the same thing, VRT. So initially it starts with some value, initial value of voltage V, ends with some 0 and some intermediate point at tau. So it will be 0.368 to V. As far you remember, as far as the last equation is concerned, you if you recall, the current expression for series RL circuit is something like this: Vt V by R into 1 minus e to the power minus t by tau. So it is exactly resembling, okay, the you see one V into 1 minus t by tau and here V by R. So equation in case of the previous one, equation actually 9, this current equation is represented by figure 4a, represented by figure 4a. So this pattern will be represented, or this pattern will represent equation 18, that is voltage drop across the capacitor. So it starts with some value 0 because initially capacitor does not have any voltage. Finally it has got some voltage V by R, or rather as per this equation 18 is concerned, it is V, and in some intermediate point after time constant t, so it becomes 0.632 V. Okay, so this is the curve it represents. So this is the VRT at after one time constant. This is VCT after one time constant. So again the definition remains as it is. Time constant is the time in second after which voltage and current becomes 63.2% of its total change. Now in case of a series RC circuit, the tau becomes R into C. Tau becomes R into C. So in case of a series RC circuit, tau becomes RC second. So we have understood the performance of series RC circuit under transient condition. We have found similar natures. Okay, so the curves are not linear in nature, they are exponential in nature, that indeed reflecting the transient behavior of the network. Okay, and time constant for series RC circuit we have found it is RC second. In case of inductor series RL circuit it was L by R, but overall conception idea of the time constant remains same. What is that? Voltage and current becomes 63.2% of its total change after that time. Okay, after one time constant time. So with this, let us end here. In the next session we shall discuss the remaining topology, which is series RLC circuit. Thank you.